Okay, now we take problem number 2. Um, Problem number 2 is telling me that I have a compressor heat exchanger arrangement, and that is I have a compressor, and this compressor is at the inlet of the compressor. I have an air, this air in, and this air has pressure 1, which is 96 kilopascal, and then I have T1, which is 27 degrees, and then I have also the volumetric flow rate given to me as 26.1, 26.91 meter cube per minute. Notice that I will put just a red around minutes because you need to be careful with the minute, with the units, because this eventually, most of the time we're dealing per second, and this problem gives you per minute is just great. Some unit problems if you don't see it, or if you're not awake enough for this. And of course, this is how the air is coming in. It's 27 is ambient condition. Again, it's ambient pressure, atmospheric pressure, and this is the volumetric flow rate. And then it goes out. You can take with blue here. It goes out, please. It goes out here at 2, and at 2 we have P2. Of course, the pressure will increase. It's a compressor. The function of a compressor is to increase the pressure, and we know that also a compressor is also increase the temperature on 27 of the air. And probably this is why, because we have this temperature which is quite high, this is why I send this into a heat exchanger before, of course, before it goes to 3, and T3 is 77 and P3 is equal to P2, because pressure doesn't change when it goes through a heat exchanger. Now a heat exchanger, I will use different color. So a heat exchanger, we know what heat exchanger is. Heat exchanger is a device, and this device is used to actually cool down one fluid, and in this case, because I want, or to heat, of course, up one fluid. But in this case, I'm interested in cooling down the air, so I send a water, cool water, we call it T, this, we call it A. TA is 25 degrees, so I send water at 25 degrees from a lake or a river, and that's gonna take some heat from the air, and it will take it out, increase its temperature, so TB equal 40, and this is where the water, so the water comes in here and goes out here. And if I take another color, I can say that Q, because this will lose Q, so we can say Q air, and this Q will be absorbed, so it will be taken by the air, so the water, so Q taken by the water, and those are equal. So that because we are assuming that this is isolated, we're assuming that I don't have any losses. So what the air is losing here is actually giving to the water there, and that's the whole process, because this is, we want to cool down the air, so we want to move or remove some of the heat there. And then the problem is asking, if you neglect kinetic potential energy changes, you need to find the power of the compressor. So you need to find the power here, input power in kilowatt, and you need also to find the mass flow rate of the cooling water. So he wants to have, I will call it mass of cooling water, just to make it different from the mass flow rate of the air in kilojoule per second. He asked for kilojoule per second, and this is why the minute here can complicate things if you're not aware. It's the problem is not in a way difficult when it's but but again, every time you have different devices, you need to take a control. I mean, you need to take one by one. And in this case, I will start by taking a control volume of the compressor, because he asked me to find the power here, and I will then take a control volume around the two fluids here, sort of heat exchanger. And if you do so, I think things might be start to look easier. So, which means that I have a compressor with inlet and outlet, and I have a heat exchanger with inlet and outlet, and then the analysis will be a little bit easier. So now some of the assumptions that we need now for the control volume here, for the compressor as a control volume, we know, we assume that there's no heat losses here. So heat, I can see heat transfer in the compressor plays no role, at least here. The other thing is that work in the heat exchanger is also equal to 0. It has no rule. So assume it's 0, and then it's also told me kinetic energy and potential energy is also 0, because it's not considered here. So those are the assumptions. And then we can go to the analysis. Now let's start with the compressor as a constant, the control volume. So that, so we say compressor as control volume. And you write the first law of thermodynamics for the compressor, and we know now that there is no accumulation of energy inside the control volume, so the rate change of the energy is equal to 0, and that is, according to the first law of thermodynamics, is Q minus work control volume plus the mass flow rate of the air multiplied by H1 minus H2. Now remember, of course, plus kinetic energy, potential energy, that is now 0, so I don't need to take it with. And this also, according to the assumption, there is no heat transfer in the compressor, and that gives you, but we have one inlet and one outlet, so M air in, or 1, equal to M air 2, equal to mass flow rate. So this is a conservation of mass. And then the work of the control volume will be mass of the air multiplied by H1 minus H2. Now the mass flow rate need to be determined. It's not given H1 and H2 need also to be determined. Now, in the previous problem, we also established a relationship between the volume flow rate and the mass flow rate. And this relation is very important, and you need to be careful because you need it most of the time. And this, the mass flow rate of the air is equal to the volume flow rate. I will write it down. Volume flow rate divided by the specific volume at 1. And that is P1 V1, and I'm talking about, again, this is volume flow rate. Please, because we have problem with the which symbol to use the volume flow rate, always remember this is a V1, but I write it here as the volume flow rate, although we don't use it here. This symbol divided by R T1, and remember where we get this from. P1 V1 as a volume flow rate is equal to M for the air RT1. This is the ideal gas law, just in a flow rate form. It's the same, but it's in, I'm sorry, it's in a rate form, and I can apply it here to find the mass flow rate of the air. So again, the mass flow rate of the air will equal to P1, which I know, a V1, the volume flow rate, it's also given, divided by R, which is constant, multiplied by T1, which is also known in the problem. And if you do so, you get this is as 30 kilogram per minute. And please notice still per minute. I can immediately divide it by 60. So if you multiply this by 60 second per minute, of course, you will get how much that in how many kilogram per second. Or you can take it to the next and just divide it by 60 when you do this. Now, if you want to, now we know that work for the control volume equal to the mass flow rate of the air, H1 minus H2. So the challenge, now we have this, I need H1 and H2. And H1 and H2 are also easy to determine because we have the temperature. We have T1, so you see here, we have T1 and we have T2. And if you convert this to Kelvin and you go to table, I can immediately come here. If you go to table, okay, this is for the water. Oh, I don't have the table here, apparently. Oh, it's here. So H1, I have the temperature. And if you go to A17, so A17 is ideal gas properties of air as a function of temperature. And you have T1 and T2, but it has to be in Kelvin. And for the first temperature is 27, which means in Kelvin that it's 300, and then the other one is for, we'll see, the other one is temperature here is 127. So in Kelvin, that's going to give you 400. So you read, this is H2. So this is H1 and this is H2. And if you substitute this here, that's gonna give you 30 kilogram per minute multiplied by 1 divided by 60 second per minute, just to convert everything to second, and that is multiplied by H1. As you can read it, it's 3319 minus 498, which is also read from the table. And if you do this calculation, you will get that the work for the compressor is actually minus 50.4 kilowatt. That is the first thing he asked us to do, is calculate the power needed for the compressor. Now for the heat exchanger, remember, for the heat exchanger you have also the air is coming in here with this state 2 and state 3 are also fully defined. And then he asked me about the mass flow rate of the water, how much cooling water or kilogram per second I need to actually cool the air from 127 to 77. That's another way how to look to it. So if we start now with the heat exchanger as my system, and I can just do it, I can draw it here so we know what we are dealing with. So I have the air coming in and then goes out, and then I have the water is also coming in here and then it goes out. There, I know the states are fully defined here and here and here. So for the heat exchanger, the mass, we can take the heat exchanger as a system now. So this is my system. And we said it's like isolated. It does no work. So we can start with the conservation of energy. With the conservation, with the conservation of mass. With the conservation of mass, mass 2 is equal to mass 3 equal to the mass of the air, actually, from the beginning, equal to the mass that we have calculated already. Now, the mass at A, remember, this is A and this is B. This is the cooling water. So the mass at A for the cooling water is equal to the mass flow rate at B for the cooling water, and that is the mass flow rate for the cooling water. I'll write it here, and that's for the areas. And now I have, with this information that I have in hand, I can now go and try to find the mass flow, because the only thing it's going to be is the mass flow rate. Because assume that, okay, I will write first the first law of thermodynamics, T divided by Tt, that's equal to 0, and that is Q minus work plus mass multiply the mass flow rate multiply by H3 or H2 minus H3, actually H3 here, minus H2 for, this is the mass of the air, plus the mass of the water multiply by HA minus HB for the water. Now, knowing this is, now we know that Q is not leaving, the work is 0, so it's as it's telling me that the mass flow rate of the air multiplied by dH of the air is equal to the mass flow rate of the cooling water multiplied by dH for the cooling water. And It's very interesting because I know that for the air I have the two temperatures, so I can always go to this table here, to the A17, and find the the enthalpies here and here. Very interesting. We go back and open this. And what we do is that I also want to finish this. So just to recall what we wrote, last thing we wrote is that the mass flow rate for the cooling water multiplied by dH for the cooling water is equal to the mass flow rate of the air multiplied by dH for the air. Now, for the air, I have the two temperatures before and after, and for the water, I also have temperature before and after. But be careful when you deal with air, you read it directly. When you deal with water, you need to be careful. The idea that because it's a compressed water actually, compressed liquid water. So I need to go to the compressed liquid tables. But we agreed, if you remember in this course, that H, for example, at 25 centigrade, which is given at the entrance, so HA at 25 is actually read from the saturated table is HF at the temperature. So if we have a liquid, and we know it's a compressed liquid, I go to the table A4, which is a temperature table. I cannot do this, I cannot read it from the pressure tables, for example, which is A5. It has to be temperature table. This is how we agreed on, or this is the minimum error that it has to do this. And you can just read HF. So if you read HF here, so this is, as you can see, this is HF at the entrance, this is HF at the exit, when the water exits. You can have and this you already calculated. This you have, so you can calculate this. And so the mass flow rate for the cold water will be the mass flow rate of the air multiplied by delta H of the air divided by dH of cooling water. And I can write air. You have this, you have this, you have this, and then you can calculate it. I don't know if I have it here somewhere. Ah, so it's here. I can write down immediately that is equal to H2 minus H3 divided by HB minus HA, and that multiplied by the mass flow rate of the air. And if you do this, you will find out that the mass flow rate for the cold water will equal to, I can write the whole thing now so you know, 40098 minus 350.49. This is the enthalpy difference for the air, and divided by 167.57 minus 14.84, multiplied by, of course, 30 kilogram per minute, multiplied by 1 divided by 60 seconds, and if you do so, you're going to get something like 0.403 kilogram per second. You see I'm going fast now because I think that we have already repeat a lot of what we are doing. Okay.